Great. So let's start, guys. So welcome all of you again for one more problem solving session. This is a problem solving session number 7 for the course NPTEL course Fundamentals of Semiconductor Devices, which is currently being conducted by Professor Digbijoy Nath. Right. Just to introduce myself again, I am SOHAM LAKHOTE, currently a fourth year Ph.D. student at Indian Institute of Science, Bangalore, and my research area is in the field of analog and RF circuits. Right. So now this was just regarding my introduction. And now again this will be the session organization. We will have a 60-minute session first, then we will take a quick 10 minutes break, and again we will resume our session. Just for the formality purpose, this will be the YouTube channel where I will be uploading all the recordings, right? And in the description section of each and every video you will find the lecture notes for that particular session. Okay, and now let's start. So let me start by turning on the laser pointer. So now we have studied a lot about the MOS capacitor. Like we had 4 lectures, right, of 30 minutes in this week. So now let's have a quick recap so that it will help us to solve the questions very quickly, right? So now we have seen what is the MOS cap structure, right? So we have a metal over here, we have a oxide over here, and this is a, what you can say, this is your semiconductor. And the reason why we are studying this structure first, because this will be the part that will be integrated into the structure of the MOSFET, right? So first we have to study this structure, only then we will be able to understand the MOSFET, right? So now what is the purpose of having this structure? So obviously we want to apply some voltages, right? We want to apply some voltages at this point as well as this point, that is the metal contact, and your semiconductor contact, that is your substrate contact, right? So now let's see what happens when you try to apply some voltages to this kind of structure, that is metal, oxide and semiconductor. So what happens when you apply a negative voltage on the gate? So for now I'm assuming that this substrate is p type. So the moment you apply a negative voltage over here, what is going to happen? It will attract a lot of holes near this interface, and this interface is called as the silicon to silicon dioxide interface, that is SiO2 interface, right? Because this is your silicon dioxide and this is your silicon, right? So if the majority carriers of the substrate, what are the majority carriers of the substrate? They are holes, right? Because your substrate is p type. So now if the holes are being attracted near to this interface, right? So that means we call that operation as a accumulation operation, right? So majority carriers are coming to near to this interface, so this is called as the accumulation. Why accumulation? Because your holes are getting accumulated near this silicon to silicon dioxide interface, right? So this was regarding the accumulation. Now you will ask me, what happens if I just change the polarity? What if I apply the positive voltage on the metal and negative on the semiconductor, right? So now this is what will happen. So assuming the same, that this is a p-type substrate, the moment you apply positive charges over here, right? So they will try to have an electric field, and this will be directed in the downwards direction, because electric field is directed from positive to negative charges, right? So electric field will be directed in this direction, and note that this semiconductor has excess holes, right? Because it's a p-type semiconductor. So since if the holes that are there, holes always moves in the direction of electric field, and your electrons always moves in opposite direction to the electric field, right? So if there are lot of holes that are present over here, then these holes are gonna get pushed into the deep. They will be pushed into the depth over here. So what is going to happen? Whatever impurities that you have brought, for example, you must have brought something like phosphorus to get this p-type doping, right? So whatever phosphorus dopants you had, whatever holes they bought with those impurities, those holes will be pushed deep into this semiconductor, and what you will be left with over here, they are nothing but immobile impurities, immobile ions, right? Completely ionized, but they cannot move at all. So you will be left with negative immobile charges that will be present over here, and that's how this electric field is getting terminated, because electric field needs both, right? Positive as well as the negative. So that's why from positive it will be starting out, and to this negative immobile charges that will be present over here in the depletion region. So this is where this electric field will actually terminate, right? So this is what is actually happening when I apply a positive voltage. So this is when I am applying a small positive voltage, right? Now what happens when I do the large positive voltage, right? So we will see that case later. So now coming to the energy band diagrams, right? So now this was the energy band diagram, and as you know, this is a p-type semiconductor. The Fermi level that you can see over here, this Fermi level is actually lying very close to your valence band, because this is your p-type semiconductor, right? And now you have a metal over here, it just has this flat line over here which represents the Fermi level, correct? It does not have that energy band gap that we see in the semiconductors, or a large band gap that we see in the oxides case. Now what actually happens? See, we want to understand, because this energy band diagram is very crucial for our understanding. We always calculate whatever we want to do, like all the expressions that we derive, many of them comes from the energy band diagram, right? So first of all, we have to see when I'm applying some positive or negative voltage at the metal, what is actually happening to the energy band diagram. The moment I apply a negative voltage over here, what did I tell you? It will attract the positive charges at this interface, and since it's a majority, it's a p-type semiconductor, the holes will start to attract over here. Now what is going to happen? You know that if I have a lot of holes, then the gap between EF and EV is actually very less, right? The more and more the more and more doping I do for the p-type, this gap that you are seeing EF and EV, it will actually shrink out, right? So now if I have a lot of holes that are coming near this interface, that clearly proves that the gap EF and EV should shrink at this interface compared to the bulk. So bulk is away from the interface and this is near the interface. So away, that is, if I look over here in the bulk region, I have this much gap. So this gap has to shrink near the surface, right? So this gap has actually shrinked over here, right? And what if I apply a positive voltage? Then I know that I'm pushing away the holes, right? I'm pushing away the holes from this region. The moment I push away the holes, what does it mean? Compared to the bulk, I have less number of holes available over here, right? If I have the less number of holes that are available near the surface, that means the gap between the EF and EV should be more at the surface as compared to the bulk, right? So I hope you got this point. So this EF minus EV should be more at the surface because I have pushed away the holes. So that's why you can see the bands are actually bending like this in the downwards fashion, because this EF and EV difference has to increase at the surface to accommodate for the pushing of the holes into the bulk over here, right? So I hope till this point it is very much clear. If you guys have any doubt, please feel free to ask me any questions if you have. Now coming, I told you this, I will come to it later. It is regarding the large positive bias. So the positive case that I told you, it was for the small positive voltages, right? So you can clearly see why it was small positive voltages, because you always remember, right? When the Fermi level is actually in the top half, that is near the EC. So if the Fermi level is between the conduction band and the intrinsic Fermi level, right? So if it is in between, then we say that the semiconductor is N type. And when do we say that the semiconductor is p-type? If the Fermi level is actually in between the intrinsic Fermi level and the valence band. So if the Fermi level is in between this region, we say that the semiconductor is p-type. If you look over here, the Fermi level that you are seeing over here, it is below the intrinsic. This is your intrinsic Fermi level, EFI. Your Fermi level is still below the EFI, right? So that means even near the surface, your material is actually still a p-type material, right? It has not inverted. But what if I keep on increasing this voltage? What is going to happen? This band bending that you are going to see, right? You know, the moment I apply a lot of voltage over here, the more these bands are going to bend, right? So now the more these bands are going to bend, then this will cross this point at certain instance, and this is what actually I am showing over here. The EFI has actually crossed the EF. If you look over here on the bulk, then the Fermi level is between the EFI and EV, and that's why your semiconductor material is still in p-type semiconductor. But the moment I look over here, you can see that your EF, this Fermi level, is actually between the conduction, that is conduction band, and this intrinsic Fermi level. And what did I tell you? When the Fermi level is in between the conduction band and the intrinsic Fermi level, you get n-type semiconductor material, right? So that means in the bulk I have a p-type semiconductor material, and in the near the surface I have a n-type semiconductor material. So what does this mean? There are lot of electrons that are there near the interface. And does it make sense? Yes, it makes complete sense, because you are applying a large positive voltage, right? So these electrons came to this to just to balance out the whatever charges you are putting at the top of the gate over here, right? So it makes complete sense that there are a lot of electrons that are present because you applied a large positive voltage, right? So I hope this energy band diagram is clear. And just to give you one more intuition, why the band should bend like this. As I already told you, there should be a lot of electrons near this interface because I am applying a lot of positive voltage. If there has to be a lot of electrons, then the gap between the conduction band and the Fermi level has to be very less near the surface as compared to the bulk. Just look at the gap between EC and EF. It is so huge over here. But if you compare over here, this gap has shrunk a lot, right? And that clearly proves that there are a lot of electrons that are present over here. So I hope even this band bending direction is clear to you, right? And now this is just for the n-type substrate that sir must have told you, right? This was for the p-type substrate that I told you, right? And this is regarding the n-type substrate. So what happens when you apply a positive voltage? What is going to happen? It will attract a lot of electrons, and since this is an n-type semiconductor, it has an excess number of electrons, so the majority carriers of this semiconductor are getting attracted towards the interface. And I already told you this operation is nothing but the accumulation, right? Because you're accumulating a lot of majority carriers near this silicon to silicon dioxide interface, right? Now what happens when you apply a small negative voltage? Okay, let me see. If I apply a small negative voltage over here, then there should be positive charges that should be coming up over here, so that there can be a electric field now, right? Now how is it going to happen? The moment I apply a negative voltage over here, the electrons that are present near this interface, they are going to get pushed away into the depth or into the bulk over here, right? So what is going to happen? You might have bought for example, this is an n-type, right? You might have bought, for example, a phosphorus with you. So this phosphorus donates the electrons, right? So now if you remove this electron out of the phosphorus, then you will be left with the immobile positively charged impurities. They are completely ionized, right? But they cannot move, so you'll be left with immobile charges, and this will create a depletion region, right? And whatever charges are there, these charges will actually balance whatever you are applying the voltage over here, right? So now coming to the why this band actually bend like those, like for the downward direction, then let's see. I already told you there has to be a positive charges that should be near the interface. If the charges that are coming near this interface are positive, then I already told you, the more and more positive charges you have, like just imagine them like something like holes, for example, right? If there are a lot of holes over here, then the gap between the Fermi level and the valence band has to shrink, right? Because the more and more p-type doping you do, the gap between the Fermi and the valence level will continuously reduce. So if I look at the bulk, the gap between EF and EV is large. If I look at the surface over here, the gap between EF and EV is reduced over here, right? And it makes complete sense, right? Because there has to be positive charges that should come up, and now because of this, the bands are bending upwards and not downwards. The downwards bands are bending like downwards and not upwards. Actually, this is a downward bending, right? So this is what I wanted to talk about. And when you apply large negative voltage, then what happens? The same case will happen. The EFI over here was always below the Fermi level. There will be some point, the voltage, where this EFI will actually cross the EF, right? And this is the part that I'm trying to show over here. The EFI has actually crossed the Fermi level over here. Now what does this mean? The semiconductor, if you look in the bulk over here, your semiconductor is n-type material because your Fermi level is lying between the conduction and the intrinsic Fermi level. But if you come to the surface, now what has happened? Your Fermi level is now actually lying between this intrinsic Fermi level over here and the valence band. So your Fermi level has shifted to the bottom half rather than the top half. So that means your semiconductor material is p-type now near this interface, and it is n-type in the bulk. So again you have formed something called as the inversion layer of the holes over here, right? So I hope this band bending, again, it is clear to you. And just to give you intuitive understanding, just look at the difference between the EF and DV over here and EF and EV over here. You will easily understand like why the bands have been bending like this and not in the opposite fashion, right? So I hope this band bending is clear to you. And now we saw some formulas, right? So we always know that for a one-sided junction, we had this kind of expression for the depletion region width, right? But what the sir told you, hey, this depletion region cannot continuously increase. At some point, it will stop, because what is going to happen? The depletion region width will only increase up to the point where your what you can say, for p-type semiconductor, your electrons are not there. Like for example, those electrons have to be generated thermally, and only when you have these thermally generated electrons, they can be attracted near the interface, right? But if those electrons are not there till that point, right, then your depletion region will keep on increasing, and there will come a point where depletion region will just stop increasing, because you have electrons that are being thermally generated, and those electrons are actually balancing whatever charge you are putting on the metal, right? So now this is what we said, like and when does that happen? So we defined one point called as the threshold voltage, and we said that the difference between the EFI minus EF that you see in the bulk over here, that is between the intrinsic Fermi and the Fermi level. Note that the semiconductor is p-type over here. This is a p-type substrate, right? So if the difference between EFI and the EF on the bulk over here, if it is equal to the difference of Fermi and the intrinsic Fermi, so EFI minus EF should be equal to EF minus EFI at the surface over here, right? So EF is higher at the surface and EF is lower at the bulk over here, right? So I hope you got this point. And now we define this point and we said that when this happens, we are pretty sure that there will be an inversion layer that will be formed, and our depletion width will not increase anymore, despite the fact that you are actually increasing the voltage, right, at the gate of the metal. Correct. And we found out that when this happens, like the what is the fires, what is the total drop that is happening across this semiconductor region. So we said that it is nothing but the total amount of band bending that is actually happening. So if I just calculate this total band bending, that is hello, so this, can you please mute yourself? Okay, great. Yeah. Sorry, guys. There was some disturbance from one of the participants. So now, what is actually happening? This was the expression of the depletion region width, right? Now, what we are doing over here? Now we said that this total band bending we want to calculate. This is nothing but your phi fp, right? Sir must have told you he is denoting this by phi f. That is the difference between intrinsic Fermi and Fermi level, and this difference is replicated over here. So now this total band bending became 2 phi f, right? And the moment I substitute phi s with 2 phi f, right, then you will get the maximum depletion width that you will be coming over here. And this phi f you know how to calculate, right? It is nothing but this kt by q ln of na over ni. So this is your phi fp, right? So now these were the basics that were necessary to solve first few set of problems, right? So now without any delay, I would like to solve few problems over here. So now just before that, let me check whether the recording is still there or not. uh, yeah, recording is still there, so we are very safe. Yeah, just a minute. Yeah. So now let me turn on my pen. Great. So now let's see what they are asking in the first question, right? So now again all the problems. By the way, guys, sorry I have not put the reference name over here. Most of the problems that I have taken, they are from the Professor Donald Neiman's book. And whenever you will see that this type of font has been changed, then those problems have been taken from the previous year's assignments of NPTEL. Okay, so these are not my own problems. These are the problems from the textbooks as well as the previous year assignment and NPTEL problems, right? So now let's look at the first problem over here. So now consider an oxide to p-type silicon junction, right? We have a p-type substrate over here because it has been given over here. Now consider it at 300 Kelvin. The impurity doping concentration is 2 into 10 to the power 15. They have given the value of Na. Calculate the maximum space charge width, and they are asking the second question: does the space charge width increase or decrease as the p-type doping concentration decreases, right? And I have just highlighted the answer over here just for your reference. So now we have already seen the formula, right? The maximum depletion width. So this is the formula for the maximum depletion width that I told you, right? The maximum depletion width, and sir must have derived this formula as well, and you can refer to the book of the Donald Neiman, right? So now we will directly use this formula, right? So now let's start. So now what is your WD max? So your WD max is nothing but 4 epsilon s, right, phi f divided by qna whole to the power 1 by 2. Now what is this phi f, right? This phi f is has not been given directly, but we know how to calculate this phi f. This phi f is exactly this phi f which I was actually talking about, right? We know how to calculate this stuff, right? It is pretty much easy. We have done it 100 times. So what is phi f? It is nothing but kt by q ln of, this is a p-type semiconductor, so I have a acceptor atoms, right? Na by ni. If it was an n-type, then I would have written nd over here, right? So now let's calculate this value. Kt by q is nothing but 0.0259, right, ln of na over ni. So na value has been given to me, 2 into 10 to the power 15, and ni we all know for silicon, 1.5 into 10 to the power 10. So if you calculate this, then the phi f value that you will be getting, it will be coming pretty close to around 0.3056 volts. This is the value of phi f that you will be getting, and now we have to put this value in over here. Correct? I hope the flow of the question is pretty much clear. So now let's substitute. Just a minute. Yeah. WD max. Correct? It will be 4. I guess let's take into the next page because this expression will be pretty much big actually. So WD max was what? 4 into epsilon. Epsilon of silicon is what? 11.9, because the depletion region is happening in the silicon, right? So you have to take the epsilon of silicon over here. 11.9 into 8.85 into 10 to the power minus 14. This is the dielectric constant of the free space, right? Into the value of phi f that we had calculated. So what is the value of phi f? 0.3056, right? 0.3056. And what was there in the numerator? Q times Na. Q is what? 1.6 into 10 to the power minus 19. And the Na concentration they have given to me as 2 into 10 to the power 15, right? 2 into 10 to the power 15. So if you calculate this value, this WD max, right? It will come out to be around 0.634 micrometer. And this is what they were asking in the question. So we have solved the first part, right? Now comes the part B, and it is very much interesting, right? So now let's see what they are asking. Does the space charge width increases or decreases as the p-type doping concentration decreases, right? So now I will just ask you guys one question, right? So now if this was a if this would have been a PN junction, correct? Let's imagine the PN junction. This is my P side, this is my N side. We have a Na doping over here, we have a Nd doping over here, right? And I have a depletion region like this. I have a depletion region over here, right? Now what I did over here, I suddenly increased the concentration of acceptor dopants, acceptor atoms, right? I made this P plus. I have a N over here, right? Now can you guys please tell me what will happen to the depletion width on the P plus side? Whether it will increase or whether it will decrease? Sorry? Decrease only. Yeah, very good. Why this happened? Because we have doped it heavily, right? And sir must have told you, when you dope a particular side of the PN junction very heavily, the width of the depletion region on that side actually decreases, right? So this is how the depletion region will look now, right? Now we will use the same analogy, and we will have our hypothesis that if I decrease the doping, what they are asking, like as the p-type doping concentration decreases, right? So what do we have? P-type doping concentration is actually decreasing. So our analogy of with the PN junction, what does it say? It should increase the depletion width. This is the analogy that we have, right? But now see, I'm a researcher, right? I have to prove everything mathematically, correct? So now let's try to get some mathematical intuition out of this formula, right? So now what is this WD max? Let me write WD max square, because there was a square root, right? So what was this? This was nothing but your 4 epsilon s phi f divided by QNA. Now phi f itself is a function of log, right? If I just put it like this, QNA, phi f is what? KT by Q ln of Na by Ni. Now we are only interested in Na. We are only interested in Na. Rest all the stuff I don't care at all, right? So now let me write everything as a constant. So for example, let me write it maybe a constant C, right? I have 1 by Na over here, right? And I have ln of Na by Ni. I hope till this point it is clear. So this function that you are seeing over here, it is looking like log x divided by x, right? Now x function that you are seeing over here, right? If I increase the value of x from 1 to 10, right? From 1 to 10, then x will get multiplied by the factor of 10, right? But if I try to take the log out of it, but if I try to check what is the value of log from 1 to 10, if I shift it from 1 to 10, you will find that this function increases very, very slowly, right? So what does this mean? If I increase the value of x, the denominator will increase with a rapid speed compared to the numerator. And if I decrease the denominator, like if I decrease it by 10 times, then the denominator will actually decrease a lot, and your numerator will decrease by a very small value, right? Now let's check. This x is nothing but our Na, okay? Because this is what is of interest to us, this parameter, right? Now they are telling us as the p-type doping concentration decreases, they are telling me that you have to reduce the x, right? So what did I tell you? The moment I reduce the value of x, the denominator is reducing very fastly compared to the numerator. So it is something like, if I had a 10 by 5, something like that, then this 5 will become immediately to 0.5, but your 10 will just reduce to some value of maybe, let's say, 7 or 8. It is something like that, right? So if my denominator is reducing very fastly, then that means my ratio will actually go up. My ratio will actually go up, and this ratio corresponded, it was proportional to W D max square. This is the ratio that I had. And what did I tell you? When the denominator was actually reducing very fast, your ratio is increasing. So again, your W D max square will increase, right? So this proves the analogy that whatever we have derived from here, right? From the PN junction, that if you increase the doping, then your depletion region size will actually decrease, the width will actually decrease. Again, we proved the same thing using the mathematics over here, and that's why the mathematics so beautiful, right? So I hope this question was very much clear to you. If you guys have any doubt, then please feel free to poke me at any point. So now this was the point, like this was the first numerical that we had. Now we had this concept of flat band voltage, right? And what was this flat band voltage? See, first we had assumed that the metal and the semiconductor have the same work function. There was no work function difference. We had seen this term called as the phi ms, right? So we assumed it to be 0. So there was no work function difference, right? But if you take the case of the real life scenario, then that won't be happening always, right? So now, so what is this flat band voltage? So now, because of this work function difference, right? The moment you have this MOS structure with you, the moment you have the Fermi level difference, right? You will be having an inherent band bending because of the Fermi difference between the what you can say, the metal as well as the semiconductor. So to cancel out the bending, we don't want it to bend inherently, right? So I don't want my MOS capacitor to be there in the depletion or inversion mode directly. I want to control that part on my hand, right? So to cancel it, to cancel that bending, we have to apply certain voltage at the gate of the metal, right? At the metal we have to apply certain voltage, so that that bending that is there, that bending gets cancelled out, right? And the voltage, the magnitude of the voltage that you apply at the gate of the metal to cancel out that bending, right? This is called as your flat band voltage, right? And this is what has been mentioned in the Donald Niemann's book as well. As a result, zero net space charge in this region. What do I mean? See, the when the space charge, let me see this space charge that you are seeing, it is existing because there, see, first there is a band bending that is present. The moment these bands are not bending, that means there is no electric field in the region, right? And if there is no electric field in the region, then what is the purpose of space charge region? If you look in the PN junction as well, there was a depletion region and there was a field associated with it. If there is no field associated, then there won't be any bending in these bands over here, right? So this is what this statement actually tells you: zero net space charge in this region, right? So I hope this point was clear to you. And now let's come to few diagrams, right? So this is what I was actually talking about, right? You had certain difference between the Fermi levels, but you applied a voltage such that this bending got cancelled out actually, right? Now we want to find out the magnitude of this flat band voltage, right? So sir must have told you whatever voltage I apply at the gate, some part of it will be getting dropped across this oxide, right? And some part of it will be getting dropped near this surface, that is your semiconductor over here. So this drop at the oxide is denoted by this VOX, not at, sorry, across the oxide is denoted by VOX, and phi s is across the semiconductor near the interface over here. Now when phi ms was 0, this equation was holding true, but the moment we have a work function difference between the metal and the semiconductor, we have to also take this one into account, right? So your total Vg becomes the sum of V oxide, the phi s as well as the phi ms, right? And now we also said, hey, what the moment you try to fabricate this MOS structure, the moment, let's say, the TSMC, the Taiwan Semiconductor Manufacturing Company, is assigned a task to fabricate this structure, there will be some impurities that will be there in the oxide, right? So this is what we were saying. And the moment there is some impurities that are present in the oxide, then they will have some net charge density, right? The moment I assume that this is a positive charge density, let's say, and this is a p-type material, this is a p-type semiconductor, let's say I don't apply anything at the gate, the moment I have a positive charges inherent in the oxide, then they will be pushing the holes that are near the interface, right, into the bulk. So inherently I will have some depletion region that will be present over here, right? And how do we get to the threshold voltage, right? First we go through the depletion, then we increase the positive voltage at the metal side up to such an extent that the depletion region will get maxed out and we get the electrons over here, right? So now if the depletion region is already there, I don't have to apply any positive voltage. That clearly means that to reach the inversion I have to apply a lesser gate voltage, that is lesser metal voltage over here, right? So the amount of effort that I need to create the inversion layer to in the SiSiO2 interface over here, the amount of effort I need if this positive charge impurities are present, it will become less actually. And that is why you can see we have a negative sign over here, because your threshold voltage actually decreases when you have a positive impurities that are present in the oxide, right? So that's why you have a negative sign that is present over here. And what did we say now? So I must have told you this. So now the flat band voltage, what is this flat band voltage will become? So this flat band voltage will be nothing but your phi ms. If these charges were not there, then the amount of bending that is happening is only because of the work function difference, right? But since there are these charges that are present now, we have to subtract this QSS dash by Cox with the phi ms to get to the flat band voltage, right? So this is the equation that we have, and we will be using this equation to solve the further numericals. I hope this is clear till this point. If you have any doubts, then please feel free to poke me at any point, right? So now let me turn on my pen. And now let's look what this question is asking to you. So now, again, the problem has been taken from the Donald Neiman. So calculate the flat band voltage for a MOS capacitor with a P-type semiconductor substrate, right? So in most of the examples, they have taken the P-type substrate. Consider a MOS capacitor with P-type silicon substrate, and they have given the doping concentration and the a silicon dioxide insulator. So we have SiO2 and its thickness has been given as 20 nanometers, right? And the gate, the metal, oxide and semiconductor, we have these partitions, right? These metal, they are not using any metal now. What they are doing, they are using the N plus polysilicon. And why N plus? Because I want this, or whatever material I am actually using, I want it to resemble very close to metal, right? That's why you can see it has been doped heavily compared to the P type substrate. It is not P plus type substrate, right? So I have to dope it heavily so that this material resembles like a metal. So they are using the N plus polysilicon gate over here, and assuming that this QSS dash, that is the charges that are actually trapped in the oxide, right? So they are telling us that there are 5 into 10 to the power 10 electronic charges per centimeter square that are actually trapped in the oxide, right? Now first of all we have to look at the formula. What is the formula? I will just write it over here. VFB is your phi ms minus QSS dash by Cox dash. So this is what we have. But do we know the phi ms? We don't have any information that is given, but they have given us a diagram on the right hand side over here. So now what is this diagram? On the y axis they have given the phi ms, and on the x axis they have given the doping concentration. And whose doping concentration? The doping concentration of the substrate. This is what you are seeing over here, right? Now I have used N plus polysilicon as my metal. So this is where my N plus polysilicon is, and there is one more N plus polysilicon that is present over here. But now what is my substrate? My substrate is a P-type substrate, right? It is a P-type silicon substrate, right? So now I have to see a graph actually which is having this combination N plus polysilicon and P-type substrate. So this is a N-type substrate, so this is not of interest to me. This is a N plus polysilicon and the semiconductor material is P-type silicon, right? So this is of interest to me. Now at a doping concentration of 10 to the power 16, at a doping concentration of 10 to the power 16, this is the point that I want to highlight. What is the value of phi ms? If you look over here, this was the value of -1 over here. This is the value of -1. If you extrapolate a little bit, you will find that this is nothing but -1.1 volt. So now we found the value of phi ms from this diagram, and it came out to be around -1.1 volt. Now what is this QSS dash now, right? See, these are the charges. See, Q is nothing but your CV, right? Q is nothing but the CV. So the moment I divide the Q by C, it should come out to be the units of the voltage, right? So this is what has been present over here. But this QSS dash, that they are not giving the charge. They are given that 5 into 10 to the power 10 electronic charges per centimeter square. This is not coulomb. This is charges, right? So that means this is the amount, this is the concentration of charges, this is not the total charge. To get the total charge, and why I want to get the total charge, because only when I divide the total charge divided by the capacitance, I will get the units of voltage, right? So I have to multiply this value by the factor of q, so that each and every charge will be carrying this q charge with it, right? So I have to multiply this number with the value of q to get this charge, the qss dash term over here. I hope till this point it is very much clear. Please feel free to ask me if you guys have any doubts, right? So now let's see. Now if I write qss dash, as I already told you, I have to multiply it with the factor of q. So I will be multiplying it by the factor of q. So what it will become? 5 into 10 to the power 10 into 1.6 into 10 to the power 19, right? 10 to the power minus 19, very sorry. So now this will become something like around 8 into 10 to the power minus 9, right? Coulombs per centimeter square. Now just notice the units. Now this is coulombs per centimeter square. This was just electronic charges per centimeter square. So we be very careful with the units when we are trying to solve any question, right? Now we have the value of qss dash. Just look at this equation number 1, right? We don't know the value of cox dash yet, right? So now cox dash was nothing but the capacitance per unit area, and it is nothing but the epsilon ox by Tox, right? We have seen this formula 100 times. So now epsilon oxide, what is the epsilon of the oxide? So it is 3.9, and I have to multiply it with the dielectric constant of the free space, 8.85 into 10 to the power minus 14. And what is the thickness that has been given to me? This is 20 nanometer, but we have to convert everything into centimeters, right? So now this nanometer will be converted into centimeters by multiplying it by the factor of 10 to the power minus 7, right? So if you calculate this cox dash, right, if you calculate it, then this value will come out to be around 1.726, right, into 10 to the power minus 7 farad per centimeter square. This was the equation number 1. Let me highlight this as equation number A. Let me highlight this as equation number B. Now what is our job? We have to substitute A and B in the equation number 1, and our question is completely solved, right? So let's do the same job. VFB was what? 5 ms. 5 ms I already calculated, it is minus 1.1 volt. We got it from the diagram, right? Minus 1.1 volt, and now minus of qss dash is what? We have to find it from the A. It is 8 into 10 to the power minus 9, 8 into 10 to the power minus 9 divided by cox dash. What is cox dash? 1.726 into 10 to the power minus 7. 1.726, just a minute, sorry for bad handwriting, into 10 to the power minus 7, right? So now this VFB, if you try to find it out, right, then this VFB value will come very close to around minus 1.15 volts. I hope it is very much clear to you. So this was a pretty easy question. The only trick was to find out this 5 ms from this diagram and the units that were given for this QSS dash, right? So these were the only two tricks that were given in the question, right? So I hope it is very much clear. Please feel free to poke me if you guys have any doubts, okay? Now this was regarding the flat band voltage, right? Now we saw one more concept of the threshold voltage. I already have given some idea to you, right? Now let's see this into the depth, because we want to solve some numericals based on this concept. Now if you look, like what I told you, like this is a p-type semiconductor, let's say, right? So now we have to apply some positive voltage over here, right? And the moment you apply, there will come a point where your intrinsic and Fermi levels that were there, like they will interchange their positions. What do I mean by that? The EFI was above the Fermi level on the bulk, but if you look near the surface, the EFI came below the EF over here. So that means this surface became more N-type material compared to the P-type material, right? But what did we say? Okay, now I will increase this voltage up to a point where this difference EFI minus EF that you are seeing in the semiconductor bulk, right? This difference will be exactly equal when at the surface over here. It is just that this difference EFI minus EF, let's say it is having a magnitude of, let's say, A. So this magnitude, even this one, that is the difference at the surface, it will have the same magnitude. The only thing is that the EFI at the bulk is greater over here. The EFI will become smaller at the surface. So this is what I was talking about. The EFI is larger at the bulk. The EFI becomes smaller at the surface, right? So now since this bending, this gap that you are seeing over here and this gap, they are exactly same. And this gap we already know, right? This is phi f, your phi f over here. right? And it is nothing but KT by Q ln of Na by Ni, given this is a p-type semiconductor. So when these two gaps are same, right, and we want to calculate how much drop is actually happening across the semiconductor, what did we say? We said that this drop that is happening, it is nothing but the total amount of band bending that your EFI is actually facing. So if this EFI is facing a 5 fp band bending over here, and it will again face the 5 fp band bending near the surface as well, right? So this 5s became equal to 2 5f over here. And your, what did we say after that? Since you have a lot of electrons that are available, when you change the voltage at the metal, this depletion width will not change now. The what will change now is that the density of the electrons that you have pushed over here, right? You bought the electrons near the silicon to silicon dioxide interface. Any change that will be happening at the metal voltage, that is the voltage at the metal, they will be reflected by this inversion layer concentration. This inversion layer is nothing but the electrons that you have bought near this silicon to silicon dioxide interface, right? So now this was the basics that we actually require, and now we had also seen some formulas, right? So now this was the charge density diagram that sir must have told you. Like if I am applying a positive voltage at the metal, right? So I have created a positive charge density over here at the metal end. So somewhere I have to bring this negative charge density, which will have the same magnitude as that of this metal, the positive charge density that I have bought at the metal, right? Now you just ignore this term now, just ignore this QSS dash as of now. Now what was happening, like your depletion region width was actually what you can say, it kept on increasing. Now it maxed out, right? And now you started having the inversion layer, that is this gray region. Just don't consider this gray region, just imagine this part over here, this small gray region that I'm pointing over here. So now this inversion layer density, because you got the electrons over here, right? So now these electrons and this depletion region, these negative charge densities are actually balancing out this positive charge density that you have at the metal, because you applied some positive voltage at the metal, right? Now what did we say? We tried to derive the formula for the threshold voltage, right? And now I won't go into the details of this derivation for now, because sir must have derived it very nicely, right? So now we have 4 terms over here in total. Just assume that these 2 terms are not there. Let's assume that the metal semiconductor work function difference is not there, and even your oxide charges are not there. Then what you have a drop across this semiconductor material, and right, and you have a, what you can say, you have this depletion region width, that this XDT, and the charges associated with it came over here, right? Now what we are saying now, okay, now we also had some band bending that happened because of the work function difference. So let's add phi ms over here. And I already told you, assuming that this is a positive, these impurities that are there in the oxide, they have a positive charge density, right? So we have to subtract this number, because some part of the depletion, some part will already be depleted because of this positive charged impurities that are there, that are stuck in the oxide, right? So these were the 4 terms that we actually had, and this QSD dash is nothing but your Q into Na into XD, right? But since we are talking about the threshold voltage now, right? So our depletion region is completely maxed out. So this depletion region width at the threshold voltage, it will remain as XDT, right? So now this is why I have put the XD, instead of putting a depletion width, I have put XDT over here, right? So now this is the value of your QSD dash over here, correct? And now if you ask me, like what is this 5fp, your 5fp is nothing but this KT by Q ln Na by Ni, we already know that. And if you look at this term, phi ms minus QSS dash by Cox, we have seen this term somewhere, right? This phi ms minus QSS dash by Cox. So let me revise you very quickly. This was the same term, phi ms minus QSS dash by Cox, right? This is nothing but your flat band voltage, right? So I hope this point was clear. And now what I will do, I will just substitute this phi ms minus QSS dash by Cox with flat band voltage, and this has been done over here. Wherever my pointer is highlighting, I have already replaced these 2 terms with the flat band voltage, right? So now this was the expression that we will heavily use for our numerical solving, right? So we will just solve, I guess, few numericals now. These are the conceptual numericals. Then we will take a short break and we will come back, right? So now let me turn on my pen over here. See, now this is a fill in the blanks kind of question, a very easy question, right? So now what they are asking, MOSFET is said to be in inversion, right? When dash carrier concentration at the surface equals or exceeds the dash carrier concentration in the bulk. So you only have 2 options. minority slash majority, and over here majority slash minority. Correct. So now if the answer to this question is majority over here in this fill in the blank, then automatically this fill in the blank will be filled with the answer of minority, right? So now can you guys just give me a small hint like how to solve this question? The MOSFET is said to be in inversion when which carrier concentration at the surface exceeds or equals to which carrier concentration in the bulk? Does the minority carrier concentration near the surface exceeds the bulk majority carrier concentration, or it is opposite? The majority carrier concentration at the bulk, majority carrier concentration at the surface actually exceeds the minority carrier concentration in the bulk. What do you think? Which one is true?
Sir,
Yeah,
in first place, there are we feel minority.
exactly. Very, yeah, very good, very good. So that means you are paying a lot of attention. So I'm really impressed. Keep on continuing like this. So he said that these are the minority carriers, and let's see the reason for the same, right? So let's see the reason. So see, this was, I already told you, this was your P-type semiconductor material, right? So now what actually happened over here? I already told you how did you differentiate between the P-type and N-type. The moment you have a Fermi level on the bottom half, that is between the EFI and EV, I told you that you consider this as a P-type semiconductor material, and the moment you have a Fermi level that is present in this top half, right? In this top half, then you say that your semiconductor material is actually N-type. Now if I check what is actually happening at the surface, I already told you this is your EF, this is your EFI, right? And this is your EV, and this is your EC. So now my Fermi level is actually between EC and EFI. So that means my Fermi level is now in the top half. So this part that you are seeing over here, right? This part, it is now actually became N-type material. And now what does this mean? There are lot of electrons that are present near SiO2 interface. So there are lot of electrons that are present near this interface over here, and these electrons are actually what? My semiconductor material is P-type. For a P-type semiconductor material, my electrons are nothing but minority carriers, right? These are nothing but the minority carriers. So minority carriers are actually getting crowded near this interface, and this is why that guy brilliantly answered this question, that we have a minority carrier concentration at the surface that will now equal or exceed the majority carrier concentration, that is your P type, that is your Na was there, right? So now it will even exceed that. So I hope this question was clear. If you guys have any doubt, then please feel free to poke me. This was very important conceptual question that I wanted to take, right? So now regarding coming to the next conceptual problem, right? So now this table below shows the different charge profiles, right? So for this question, you want to focus only over here. That is for this problem that is present on this slide, right? And now what they are asking, depending on the charge profiles that have been given, identify the biasing conditions for the charge diagram shown in the left column, right? So now can anyone please tell me whether this diagram that you are seeing over here, this first diagram of the charge density that you are seeing over here, what does it consist? Is it operating in the depletion mode, accumulation mode, or is it in the inversion region? So can anyone please help me to solve this question? This red thing that you are seeing over here, it is nothing but the space charge region. Let me light. This is nothing but your depletion width. And this green one that you are seeing over here, these are actually your what you can say, this is a P-type material. Let's say assume this is a P-type semiconductors. So this green things that you are seeing over here, it is showing that there are a lot of electrons that are present near the silicon to silicon dioxide interface. So now after giving this hint, can you guys please tell me, the first diagram is actually hinting you towards the depletion, inversion, or accumulation?
First one is
Correct. And what about the second one? Depletion, exactly. Very good. So this is the answer that is correct. So very good. So now this question has been solved. And now the second question, what it is asking, the match the correct charge diagrams equivalent to their corresponding electric field plots. Right now, this will be a little bit tricky, so hold on with me. Right. So now, just a minute. Let me draw it very quickly. So now this is my oxide, this is my metal side, and this is my semiconductor side, right? So now what was the charge diagram that was given to me? I had a sheet of positive charges, that is plus Q, that was given over here. There was nothing in the oxide. There was no impurity that was there in the oxide, right? And if I just consider, for example, a depletion region for now, right? So let me consider a depletion region. Let's assume that it is not inverted as of now. So now this is the negative density that I have. This is minus Q, right? And this is your W depth. And this is your rho, y-axis, and this is your x, right? On the x-axis. Now, how do you find the electric field profile from the charge profile it is given to you? You integrate it, right? You integrate it and just forget about the constant as of now, because they are not asking us the value. They want the shape of the profile, right? So now what I told you over here, the moment like this charge density that you are seeing over here, there is actually no width that is present. This delta W is actually zero, because metal had so many free states that are available, that whatever charge density it want to accommodate, it will just accommodate in a aerial kind of shit. It doesn't require any depth, it doesn't require any width over here, right? So it can, you can consider it like a impulse function. You can consider it like a impulse function. So now the moment I try to integrate this profile over here, so till this point I will just project them downwards, right? So now let me highlight this as point number A over here, and let me highlight this as point number B. This is my origin, right? And this is my oxide, this is my metal, and this is my semiconductor. Till this point the integration was zero, right? Because there is nothing present over here. The moment I have a positive impulse function that is present, right? So now suddenly the integration of delta t of t dt, right? From minus the moment you integrate the delta function, right, you get a sudden jump. What previously when I had asked this question, what is the integration of impulse, somebody had stated that you get the what you get the unit step function, right? So for example, the if I just integrate the delta function, you will get this step function, and the moment you integrate the step function, right, you get a ramp function, right? So these are the basics from the signals and systems I will be using. So the moment I integrate the delta function, that is the impulse function that is present, I will get a sudden jump. And I will be over here, correct? I will be over here now. Now there is nothing in the oxide, right? There is nothing in the oxide. So whatever I have integrated till now, this value will hold on. This value will hold on till the end of the oxide. I will reach the interface over here now, correct? Now there is a negative charge density that is present over here, and it is having the value of minus Q over here, right? Now the moment I integrate a constant value, right, the integration of constant value, again just look over here, what I told you, it is constant over here, so I will get a ramp corresponding to it. But if this constant is negative, if this constant is actually negative, then you will get a decreasing ramp. Guys, just a minute, just give me a second. Yeah, so now it will give me a decreasing ramp, right? So now since I'm integrating a negative value over here, like I will have a linearly decreasing function, right? Now, but just to tell you, sir must have told you, this is my oxide, this is my semiconductor, right? So the only thing that is continuous between this interface is your flux. You must have heard like this d1 is equal to d2. What is this d1? This is nothing but the epsilon 1 times e1 is equal to epsilon 2 times e2. So sir must have told you this, right? The only thing that is constant across this interface is the flux. Electric field is not continuous because of the Maxwell's equation. So when you will be going into the third or fourth year, right, you will study this Maxwell's equation, and you will study the application of Maxwell equation for the boundary conditions, right? So this is nothing but the boundary, because I have on one side I have a oxide, on another side I have a semiconductor, right? So this has its own epsilon, it has its own epsilon. Now what happens when electromagnetic field actually tries to penetrate this region, right? So some things happen, and to understand what actually happens, you have to apply the Maxwell equation. So just remember this now, that electric field is not continuous across this interface. The only thing that is continuous is your flux, right? And the flux is given by epsilon times E, right? So now since the electric field is not continuous, now what I have to show over here, that there will be a drop in the electric field. There can be drop or there can be increase, right? Now how will I decide whether there will be a drop or increase in the electric field? This equation will actually help me, right? So now I will apply this equation for this oxide semiconductor interface, right? Epsilon oxide into field in the oxide is equal to epsilon of silicon into the field in the silicon, right? This is the EOX. This is the EOX I know. I don't know the value of ESI. I don't know how ESI will look like, right? So let me take it on the left hand side. ESI will be nothing but epsilon oxide upon epsilon of silicon into EOX, right? Now this epsilon oxide is just 3.9 and this epsilon of silicon, it is around 11.9. So this ratio is, so if I just take it, if I just tell you ESI upon epsilon of oxide, this ratio is always less than 1, right? So that means the electric field in the silicon, if it is not continuous, then it will start at a lower value compared to the electric field of oxide. So I was showing you 2 points, right? Let's say this was my point number 1 and this was my point number 2. I was confused, like I know the electric field is discontinuous, but I didn't know how to show this discontinuity, whether this discontinuity will go up from here to here or whether it will fall down. Now I have proved you that the epsilon of the electric field in the silicon will indeed be smaller compared to the oxide. So now my graph will actually start from here. So this is what my EOX was, right? Now it will fall down immediately it will fall down. And since this is the integration of this negative constant is a decreasing ramp, which I have shown over here, right? So I will have a decreasing ramp actually. So this is how your diagram actually look. This is not a parabola, this is a ramp. Just because my drawing is not good, I'm not able to draw it properly. So just a minute. This is your ramp actually. This is a ramp function. Sorry for the mess that I have created. So I hope it was clear. Let me change the color actually, and I will just retrace the graph that I have drawn over here. Okay. Where is the ink color? Blue one. Yeah. So now let me retrace it. So till this point it was 0 over here, right? There was nothing present. Now because there was an impulse function that I got at the metal oxide interface, it suddenly jumped upwards, right? Because of the positive value. Then there was nothing in the oxide. That's why it remained flat over here. We found out that the electric field cannot be continuous across this boundary because of the Maxwell's equations, right? And so now there has to be discontinuity. We use this flux. The flux will remain constant, right? We said the flux will remain constant, and that's why we found out that the electric field in the silicon will actually be lesser compared to this EOX. So that's why we had this negative kind of jump over here. And from there on, what I told you, the moment you integrate the negative constant, right, you get the falling ramp function, right? So that's why our electric field actually failed like that. It failed like this, right? It failed like that, correct? So now we have to just see whether we have this kind of electric field diagram in the options or not. So if you look over here, right, you are seeing these two options, this option number C and option number D, right? So now this has to be the answer, correct? Now these diagrams, the other diagrams that I'm telling you, these are not making any sense, so we will clearly reject them, the A and B. Our profile shape has to just a minute. Yeah, our profile shape has to be like that. It should be constant across axis and there should be a sudden negative jump and then a linear fall should be there. So only these two options are actually matching, right? And now to differentiate actually which one will be corresponding to what, right? So now let me just change the ink color, maybe back to red over here. See, there is a negative impulse function that is present. If you look in the figure 1, right? If I just zoom it, right? This is my oxide. I already have certain negative impulse function in the charge density that is present for the figure number 1, right? So I already told you we have to always integrate, right? So now when this impulse function was not there, like this is my oxide, right? This is my EOX, right? It fell to this ESI value over here, and after that I had a linear fall. Let me highlight this as point number A. Let me highlight this as point number B. And this was when no impulse function was present. No impulse in the p-type semiconductor. In the p-type semiconductor, right? But now I have this impulse function that is present for the figure number 1, right? So for figure 1, let me highlight this for figure number 2, because this was for figure number 2, right? Correct. Now when this impulse function is created, I already told you, like when I integrate a negative impulse function, I get a negative unit step function, right? So now this jump that you are seeing over here, this negative jump, actually it will get added up with this difference between the point number A and B that you are seeing over here. So now if I have a EOX like this, correct, then this fall that you are seeing between the points A and B, right, it will be very sharp. This is my point number A, this is my point number B, and then you will have your linear fall. Correct. So now what did I say? Because of this negative impulse function, the difference between the point number A and point number B, actually it will be huge, right? For wherever I have the where I have this negative impulse function. So now if I compare the C and D over here, again you can see, let's say this is first point, this is point number A, this is point number B. Again over here if you look, we have a point number A, we have a point number B. So this difference is clearly smaller in figure number C compared to the figure number D. So wherever the difference is higher, that means I am actually having a negative impulse function, and this is the case with figure number 1 actually. So this D that you are seeing, it corresponds to figure number 1, and this C that you are seeing over here, it actually corresponds to figure number 2. Right? So this was the answer for this question, right? So you can match it easily because we have completely solved this question, right? So you can match this figure very clearly. I have written the I have already written the answers over here, right? This is for figure number 2, and this is for figure number 1. So I hope the question was very much clear. So by the way guys, we will just take a very short break now. So now we will be back at 7:15 sharp. So the break starts now. If you guys have any doubt, then please feel free to poke me now. Yeah, we are recording. Great. So now we have solved few problems, right? So now the main thing now that we should do is let's solve few gate problems, because this is the main motivation, like behind doing this course, right? So now let's try to solve a problem that came in gate EC 2014, right? So now let's see what has been given. An ideal MOS capacitor has a boron doping. Boron is what? It is an acceptor atom, right? The Na concentration is given as 10 to the power 15 in the substrate. So it's a p-type substrate. When a gate voltage, that is, if you just consider this as a MOS structure, so the gate voltage is nothing but the Vg that you apply actually at the metal. Okay. So when the gate voltage is applied, a depletion region of width 0.5 micrometer is formed with a surface potential. What is this surface potential? So you must have seen this term called as SHIS, right? What did we say? Whatever gate voltage we apply, it actually drops across the oxide and it drops across the semiconductor, right? The surface potential, right? So this SHIS is what they are talking about. It has been given as 0.2 volts, right? And this is when the depletion width is around 0.5 micrometer. Now given that they have given the dielectric constant of the free space and the relative permittivities, right? The peak electric field in the oxide region, right? They are asking us to calculate the peak electric field in the oxide region. So I had already shown you the graph, right? This is what the electric field profile looks like. So it drops suddenly, and then again we have a linear fall, and this is your ESI, correct? And this was your oxide, and this is how our electric field graph looked actually, right? X versus electric field, E of X. So now this, they are asking the peak electric field in the oxide region. So that means they are asking us this flat value of EOX over here. Now let's see how can we solve this question. So now let's see what formulas we have. So we know, like, this peak electric field, right? The peak electric field, that formula that you must have seen, right? We have studied it in the one-sided junction as well. So it is nothing but your Q into Na into XD divided by epsilon S, where this depletion region is forming. That's why this should be silicon, right? This formula we have seen, right? And one more formula that you must be knowing, that I must have told you, right? So let's say this is your electric field profile on any side, for example, and this is your peak electric field. Let's say this is your ESI, right? And this is your XD, this is your XD. So how to calculate the potential? You always integrate it, right? So this integration will yield nothing but the area of the triangle, and it will be half into ESI into XD, right? And since this is happening on the semiconductor, that is on the silicon side, this is nothing but your surface potential. So the moment I combine this formula with this, what I get, psi s will be equal to half QNA upon epsilon s into xd square. I'm damn sure sir must have told you about this formula as well, right? But let me check whether do I actually need this formula or not. So I already know the value of what you can say the xd has been given to me. The surface potential has also been given to me. I can easily find out the value of ESI from here, right? So what is the value of psi s? 0.2 is nothing but half into ESI into xd is 0.5 micrometer. So 0.5 into 10 to the power minus 4, because we always want to convert everything into centimeter, right? So this ESI value, if we calculate, then this ESI, this will come out to be around 0.8 into 10 to the power 4 volt per centimeter. Now this is what we have. The field in the silicon, the ESI, just a minute, sorry, the ESI, right? This peak ESI value that I was actually telling you, this is what we have. Now, if I know the field in the silicon, how can I know the field in the oxide? Because my question is not asking me ESI, it is asking me EOX, right? And I already told you in the last slides, right? The even though the electric fields are not continuous across this boundary, that is the oxide and the semiconductor boundary, my electric flux, that is D is equal to epsilon E, is continuous across the boundary. And this is what this is nothing but the application of Maxwell's equation for the boundary condition that you will be studying in the later engineering courses, right? So what do I have? Epsilon of oxide into the field at the oxide will be equal to epsilon of silicon into the field, the peak field in the silicon, right? And we want EOX, right? So EOX will be nothing but epsilon Si divided by epsilon oxide into ESI, right? I know everything now to solve the value for EOX, right? Epsilon Si I already know it is nearer to 11.9. The I guess I don't have to use that because they have given the values of 12 and 4 over here, right? So this 11 point exact value is not needed. So I will just use the value of silicon as 12, the dielectric constant. The epsilon ox, they have told me to use the value of 4, or else I would have used 3.9 over here, right? But I don't have to do that. And also ESI I already know, right? zero point 0.8 into 10 to the power 4. This is what we have calculated. So the moment you solve this question, right? The moment you solve this numerical, this value will come out to be around, let's say this 4. So this will come out to be 3 over here. So it will come out to be around 2.4 into 10 to the power 4 volts per centimeter, right? They are asking the question for volts per micrometer, right? So now this 10 to the power 4, if I just vanish it, right, then this will become as 2.4 volt per micrometer. This is the field that you will be able to see in the oxide, right? This was the gate question, not very hard, not very easy as well, right? It involved the application of this, the flux is continuous across the boundary, right? So I hope this question was clear. If you guys have any doubt, please feel free to poke me, especially in the gate questions, right? Now again we will take one more interesting problem from the gate 2016 that came, right? So a voltage VG is applied across a MOS capacitor with metal gate, right, and a p-type silicon substrate, and the temperature has been given to me. Now they have mentioned one term called as the inversion carrier density, right? I will come to it what this thing is actually, right? Or for VG is equal to 0.8 volts is 2 into 10 to the power 11. For VG is equal to 1.3, the inversion carrier density is 4 into 10 to the power 11. Now the value of the inversion carrier density has been given for two different gate voltages, right? And now they are asking, now what will be the inversion carrier density when my VG is actually equal to 1.8 volts, right? So now let me tell you what is this inversion carrier density. See, if I have a capacitor with me, right, a simple capacitor. So if I have a Q charge, positive Q charge on one plate, then I have the negative Q charge on another plate, right? Now what is actually happening in the MOS case? Let's say this is my M, this is my oxide, this is my semiconductor, right? Now what is actually happening? I am applying a plus QM charge over here. For example, I'm applying a plus qm. Why m? Because this is for the metal, right? And let's say I'm applying qm dash. Why qm dash? Qm dash is nothing but the charge per unit area, right? So now I'm applying plus qm over here. Now what is actually happening over here? There are actually two things that are balancing this out. One is the depletion region itself, right? One is the depletion region itself. It is having a width of xd, and now there is a inversion layer that is actually getting formed. There is this inversion layer that is actually getting formed, right? So now if I call, for example, if I just tell you what is the charge associated with the depletion region, then you will tell me, sir, it is nothing but q into na into xd, right? Now I will denote this thing as q dep dash. I denote this qna into xd as q dep dash, and the charge density associated with this inversion layer, I will denote this as q inv dash. I hope this is clear. And if I balance the charges on both the sides, and since there is no impurity that is present in the oxide, right? So now my qm dash, right? It has to be equal to q inversion dash plus q depletion dash. And now do you know this is a negative sign? Like these are the electrons, but I am applying a positive sign over here, right? So these magnitudes can't be just equal. We have to have a negative sign over here, because these are positive charges at the qm and there are negative charges at the q inversion and the q depth side, right? So now this q inv dash, this is what you are seeing, right? This is what they are actually telling you. This is the inversion carrier density, that is 4 into 10 to the power 11 per centimeter square for Vg is equal to 1.3 volts. So I hope what is this value is clear to you now. This is nothing but this q inversion dash actually, right? So now we know one more thing, right? So for this capacitor, that is our normal capacitor, I know this is q is nothing but cv, right? And how we got this? We are applying a q charge, like we have a q charge on one plate, right? And now we have a v over here, the voltage difference between the two plates, right? Whatever voltage difference I'm applying, right? So now we know this is q is equal to cv. Now if I try to do it same for the case of the oxide over here, right? If I just look, it is also a capacitor, right? Now what will replace this q? This q that you are seeing over here, it will be now replaced with qm dash, because we have a qm dash positive charges over here, right? Now this c that you are seeing over here, right? This c that you are seeing over here, since the inversion layer has already been formed over here, right? So this will be nothing but the c of oxide, right? We have seen that cv curve, right? We have seen that cv curve, it falls and it comes back over here, right? After this is nothing but your vt point, right? So now since the inversion layer has formed, now the whatever voltage change that will apply over here, this will be reflected by this invert change in the inversion layer charge, not with respect to the depletion charges, right? So this will be cox over here. And what about the v over here? V is nothing but the voltage difference that you are having across the oxide, right? This is what is forming your capacitance. So this is nothing but your vox, right? So now once this is very much clear to you, now what I will be doing from this equation, I will rearrange this like vox is nothing but your qm dash divided by cox dash, correct? And now I already know qm dash, right? So now my vox will be what I'm doing, this qm dash I will be substituting over here, right? So this vox will be nothing but minus of q inversion dash plus q depletion dash, right, divided by cox dash. Just bear with me for a few minutes, I will tell you why I'm doing all this stuff, right? So now this is the vox, right? But we also know one thing: whatever gate voltage I apply, it has to get dropped across the oxide and the surface potential, right? This psi s. But I already have found the equation for vox, right? From the previous slide, if I look at the vox, then this is the vox that I want to substitute, right? This is the vox that I have. So now let me use this equation now, right? To substitute in place of Vox. So what I will have, I will just open up that bracket, minus of Q inversion by Cox dash, right? Minus of Q depletion dash divided by Cox dash plus psi s. Now this is what I am left with actually. And now if you carefully look at this term, right? Psi s minus this Q depletion by Cox dash, this is nothing but your threshold voltage. Assuming phi ms is 0, assuming there are no oxide charges that are present, this is resembling to your threshold voltage formula, right? So now what it will become like, Vg will be nothing but minus Q inversion dash divided by Cox dash plus threshold voltage. Now if I write Q inversion dash will be nothing but your minus of Cox dash into Vg minus Vth. This is what I wanted. This is what I wanted, and that's why I did all this Ramayana and Mahabharat. This is the equation that I wanted actually, right? And again, it's the same kind of equation, right? Q is equal to CV kind of equation, right? You can clearly see this is nothing but the difference in the voltages, right? So now once I have this equation with me, now let me check what is given, right? And why we did this, because see what was the asked in the question, what was given in the question, for a particular value. Just a minute, where is my stylus? Yeah, for a particular value of Vg, they gave me the value of Q inversion, right? Now let me check whether I have equation arranged in that fashion or not. For a particular value of Vg, I have a value of Q inversion with me, right? So they have given this for two cases, right? So now what I have to do, this is nothing but a linear equation, right? I don't know the values. See, for example, this is not known to me. Even the Cox dash is not known to me. So what you have to do, you have been given two cases. For one Vg you know the Q inversion dash, for another Vg you know that Q inversion dash as well. So you have to solve these two, you have to solve the linear equations, two linear equations, you have to, and you have to find the value of Vth and this Cox dash, right? So now I will try to substitute everything into this equation. Let me write it as equation number A. So for the first case, when the Vg was 0.8, my inversion layer charge was around 2 into 10 to the power 11. Note that this is a negative charge, right? So that's why I have to write a negative sign over here. Minus of 2 into 10 to the power 11 is equal to minus Cox dash, and the Vg was 0.8. 0.8 minus Vth. This is for the first case, so let me write it as equation number X. And for the second case, when my Vg was 1.3 volt, my inversion carrier density is 4 into 10 to the power 11. So now let me substitute it, right? Minus of 4 into 10 to the power 11 will be nothing but minus of Cox dash, and again my gate voltage was 1.3 volt in this case, Vth. So now you have to solve this. I will just write it, solve x and y linear set of equations, not linear set of equations, set of linear equations, correct? So from there I will get the value of Vth as well as Cox dash, right? So I will just leave this as a homework for you guys. So the value of Vth that you will be able to find out, this Vth will come out to be around 0.3 volts. So this is what you will be getting, 0.3 volts, and the value of Cox prime that you will be getting, it will be coming close to 4 into 10 to the power 11. And this is unit is what, farad per centimeter square. This is a capacitance, right, per unit area. So these are the two values that you got, right? So now the question that they ask, now we know the each and every unknown parameter in this equation. In the equation number A, there were two unknowns, Cox dash as well as the Vth. We have already found out them, right? So now our equation became something like, the Q inversion dash will be nothing but minus Cox dash is 4 into 10 to the power 11, right, into Vg minus 0.3 volts. Now this is the equation that I will be working with. For any particular value of Vg that the question will ask me, I will easily be able to find out the value of the inversion carrier density now. And this is exactly what they are asking. What is the value of inversion carrier density for Vg is equal to 1.8 volts, right? So now let's substitute Vg is equal to 1.8 volt over here. This is minus 4 into 10 to the power 11. 1.8 minus 0.3, right? This will be nothing but your Q inversion dash, right? So if you find out this value, right, this Q inversion dash, if I just take the magnitude on both the sides just for the simplification, this will be coming out to be around 6 into 10 to the power 11 per centimeter square. I hope this question was clear to you. A very important question, a little bit tricky question if you had just studied semiconductors till now, right? So, but this formula that I derived in front of you, right? Sir will again take it in the concept of the MOSFET as well. I will just write it. Concept of MOSFET. So you will be seeing this formula frequently being used in the, what you can say, the current equation of the MOSFET. So this formula is not just limited to this question. You will be using this formula a lot even to derive the current through the MOSFET, right? So please don't forget this formula. Just note it down somewhere in your notebook. So now I hope till this point it is very much clear to you. All the questions are very much clear to you. By the way, I have few questions left in between, but I want to cover one question on the CV characteristics as well, because I haven't covered any question on this topic, right? So now let's cover the some concept of the CV characteristics so that it will help us to solve the numerical, right? So now we have studied the CV characteristics, and what did we say? What is this capacitance actually? So for any particular small change in the voltage that I will apply across the metal, right? So I will get some differential charge increment in differential charge addition over here, right? So on top of this charge density, this dq dash got added over here, and correspondingly the positive got added just to balance it out, right? So now what is actually happening, what we are trying to check, okay, I have three modes of operation. One is accumulation, one is depletion, and one is my what you can say the inversion mode of operation, right? So across all accumulation, so across all these three modes, like I will see what is the energy band diagram, and I will see what is the charge density profile, right? Because capacitance is having two components. One is coming from the oxide itself, and another one will depend on whether it is operating, whether it is already crossed the inversion or not. Like if it has not crossed the inversion, then the depletion region width will determine the capacitance, right? And if you are already crossed the inversion, right, then whatever charges that, whatever voltage that you apply, these changes will be easily reflected directly over here. So consider the first case, accumulation mode. So whatever changes that I'm applying over here, like if I apply for example any particular voltage, right, immediately these opposite kind of charges will be creating over here, because this is a p-type semiconductor, right? The moment I apply a negative voltage over here, all the holes, many holes will get attracted toward this SiO2 interface, right? So all the action is happening near the interface over here. So whatever change that I gave, for example, whatever voltage change I applied, correspondingly there was a change in the charge, and corresponding to the change in the charge at the metal, I got the opposite change in the charge in the oxide to semiconductor interface, right? Now this is one point. Now the moment I go into the depletion mode, in the accumulation I was applying a negative voltage at the metal, but in the depletion mode I am applying a positive voltage at the metal. At the moment I apply positive voltage, the few of the holes that are near this interface, they will get actually pushed out, right? And because they got pushed out, we are left with the immobile atoms, immobile charges, right? Which created a depletion region over here. Now what happened, whatever positive, let's say I increase the voltage, right, corresponding to the increase in the voltage, I got the increase in the charge at the metal oxide interface over here. Now to balance this charge out, this charge will be balanced not at this end, not at this oxide to semiconductor interface end, but this charge will be balanced at the farthest end, that is at the end of the depletion region. Now just see the difference over here. The previous case, whatever charge I was applying at the, whatever change in the charge happened at the metal, the corresponding change happened right at the interface, right? But over here if you look, the whatever change is happening at the metal oxide interface, the change is happening at a farther place, right, at the end of the depletion region. So now this became like my two plates of the capacitor, and in between I have this oxide as well as this depletion region, right? So now this is a case like where I have put two capacitors in series, right? And the moment you take the two capacitors in series, then what is the effective capacitance? It is nothing but this the what you can say the parallel combination of these cox values, right? The capacitance value, the C1 C2 divided by C1 plus C2, right? So now this is what we are using over here. So now if you simplify this thing over here, if you just divide this numerator and denominator by this CSD dash, right, you will be left with this equation over here. And now if I just replace Cox by epsilon ox by Tox, right, Cox is nothing but epsilon ox by Tox. Similarly I can do for the CSD as well, right? For CSD this is the depletion region width, this is the epsilon ox is replaced by the epsilon Si, because the depletion region has been formed in the silicon, not in the silicon dioxide, right? So that's why you are seeing the epsilon of silicon over here, and the width of the depletion region XD will be nothing but the thickness over here, right? So that's why you got the XD over here. So I hope you guys got familiar with this equation till now, and this is what sir must have told you, right? Now a very interesting case, right? A very interesting case, what actually happens, like, so when you apply a lot of positive voltage, I already told you, like this you will start getting a lot of electrons at this interface, and whatever change that you were expecting to hear, that it should have happened at the farther end of the depletion region, now this change will actually start to happen just at the interface, because you have created a inversion layer over here. You have a lot of electrons that are present, so they can respond very fastly the moment you do any change over here, not with very high frequency, right, with a very small frequency only. The moment you do any change over here, it will be reflected over here, right. Now coming to this case, that's why your capacitance, right, it again got, it became equal to the oxide capacitance. But over this case, right, what actually happened, so sir told us to derive one thing, the minimum capacitance. Now when the minimum capacitance will happen, when your xd, just look at this equation, when your xd will be maximum, your denominator will become maximum and your c will become minimum, right. So I have to find a case where my xd becomes maximum, and we have already seen the case, right. This we have already told you that this difference, that the band bending that you are seeing, when the band bending is nothing but 2 times phi f, we saw that the EFI minus EF is nothing but your phi f, and when your band bending is nothing but 2 times this phi f value, you will have the maximum depletion width over here. So the moment I replace this xd with the maximum depletion width, I have to replace this c dash with c minimum dash. I hope this point is very much clear. And if you ask me to calculate the value of the maximum depletion width, then you will be using this formula, and I'm damn sure sir must have taken it in the lecture as well, right. So this is a background that we actually require to solve the numerical. We will be just having one numerical on the CV characteristics, right. So I hope till this point it is very much clear to you. And this is the total CV characteristics that sir must have explained you. First, we have a accumulation, right? The capacitance exactly remains constant, equal to Cox, right? Again, at after applying a very high gate voltage, we, what I told you, like even though you have a depletion region, but whatever change that you want to do over here, it is not happening at the farther end of the depletion region. It is actually happening right at the interface over here, right. So now because of that, you got again your capacitance actually got increased, right. And over here what is actually happening, your two capacitances are coming in series, and you know, the when you put two capacitances in series, right, the capacitance will be lower than the lowest value of the capacitance. Just like when you put the, what you can say, 2 and 2 ohm resistances in parallel, their parallel combination yields a 1 ohm resistor, right. So the parallel combination of the resistor is smaller than the smallest value. Similarly, a series combination of capacitances is smaller than the smallest value of the capacitor. That's why your capacitor is actually decreasing over here, right. And you have to use that equation to actually get this graph, right. And exactly at this particular point, you have your threshold voltage point where your what you can say, you have created a very strong inversion layer near the silicon to silicon oxide interface. So I hope till this point it is very much clear. And now I guess sir may not have told you, this was with respect to the p type substrate, right. But if I change the substrate to n type, then what will happen, right. I already told you, when you apply a negative gate voltage, you get the accumulation for the p type substrate, right. So let me just draw a very quick drawing over here, just a minute. Yeah, so let's say this is your metal, let's say this is your oxide, right, and this is your, let's say, semiconductor, let's say this is the n type. Now electrons are the majority carriers, right, electrons are everywhere, correct. Now what I told you, the accumulation is the case when your majority carriers actually move near the SiO2 interface. I want these electrons to move near to the interface, so I have to have a positive charges over here. I have to apply a positive voltage over here. Only then the electron from the bulk will be attracted near the interface. And this is what you can see over here. When my Vg value is very, very high, right? When my Vg value is very, very high, I am operating under the accumulation mode. Whatever voltage I will apply over here, immediately a differential charge dq dash will be developed right at the interface, right. That's why my capacitance is actually higher, because it is representing the oxide capacitance, right. This is my cox level actually, right. Now what happens if I do very opposite, what happens if I apply a very large negative voltage, then a large number of electrons will be getting pushed away from the SiO2 interface. I will be left with the positive immobile charges. I will also be having a inversion layer of holes. So how it will look like, so you will get a impulse function, positive impulse function, right, because you are attracting a lot of holes. And you will also have a depletion region as well. You will also have a depletion region over here to balance out the negative charges that you are putting on the metal, right? So now again, if I apply a very large negative voltage, right, then this depletion region will cease to what you can say expand further. You will reach the xdt maximum value that I told you, right? You will reach it, and after that, since you have a lot of holes that are there near this interface, any change, any differential dq that you will apply over here, it will be immediately getting reflected over here, right? So that's why for very large negative voltage, I am again getting the same capacitance cox, right? And this is the maximum capacitance that you can get. And in between, what will happen, in between you will have your threshold voltage point particular to over here. Just note that this vt is actually negative when you have a n type substrate, right? And the vt that you will be seeing over here, right, this is the vt, this vt is the positive one. So the moment I give you a CV characteristic diagram, let's say I give you this kind of diagram, the CV characteristics, then you should be immediately able to identify whether my substrate, the semiconductor substrate, is P type material or N type material. If my VT, let's say, if it is negative, that means I have used the N type substrate, right? So this is my substrate, and the moment my VT is actually positive, that means I have used the P type substrate. I hope this is clear to you. This is very very important because in lot of competitive exams they will just fool you, and after solving the question you will come to know that the substrate was not actually N type, but it was actually P type, or vice versa, right? So please remember this. Just see this VT point and just see whether it is a negative or a positive, and from that you can actually identify the substrate, right? So now these were the basics that we needed actually to solve this particular numerical from the Donald Niemann, right? So now let's try to see what has been given in the numerical. So now this numerical is asking us to find out the following things. They are asking us to find out the value of cox and Cmin dash. I already told you what is this Cmin dash, right? The moment I maxed out the my depletion width, my capacitance will reduce down to its minimum value, right? So these are the formulas that I have written over here, and sir must have taken both of these formulas, right? So now let's start with the easy one. So what is the cox? Cox dash is nothing but epsilon ox by Tox, right? And what is epsilon ox? It is nothing but 3.9 into dielectric constant of free space, 8.85 into 10 to the power minus 14 divided by the Tox. What is Tox? Tox is nothing but 18 nanometers, so 18 into 10 to the power minus 7, right? Now this value, if you try to solve it, this value will come out to be around 1.19175 into 10 to the power minus 7 farad per centimeter square. This is the first question that they had asked me. Now coming to the Cmin dash, right? See, let me check whether I know each and everything to find out the value of Cmin dash or not, right? Cmin dash. So if you look in this formula, I know the value of epsilon ox, I know the value of Tox also, I know the value of epsilon s also. What about this xdt? No, I don't know the value of xdt. I have to find out the value of xdt. Is there any formula available with me to calculate the value of xdt? Yes, the formula is available over here. Now, do I know all the parameters in this equation to calculate xdt? Let me check. The value of doping concentration I know. The value of constant Q I know. Again, the epsilon s value I know. But what about phi fp? Again, the phi fp I don't know, right? So again, I have to use the formula for phi fp. Do I know any formula to calculate the phi fp? Yes, phi fp is nothing but your difference of what you can say, your EFI minus EF, right? And this is nothing but your KT by Q ln of Na by Ni. I hope you remember this formula. Now let me check whether I know everything to calculate the value of phi fp or not. KT by Q I know. The acceptor concentration have been given to me. Ni I know, right? So I will first calculate the value of phi fp. Then I will substitute it in the depletion region width formula, and from there on I will calculate the value of Cmin dash. Okay. I hope the flow is very much clear to you. So now let me start with the phi fp. Phi fp is nothing but KT by Q is nothing but your 0.0259, right, into ln of what is the value of Na. Na is 10 to the power 16. What is the value of Ni? 1.5 into 10 to the power 10. The moment you substitute this value, right, this value will come pretty close to around 0.347 volts. This is the value of phi fp that you will be getting. Now this value I will use in the XDT formula, right? So now let me write the formula for XDT again. So x dt is what? It is nothing but the square root of 4 times epsilon s phi fp divided by qna, the whole to the power 1 by 2. So now let's try to substitute everything. 4 into, what is the value of epsilon s? Epsilon is nothing but 11.9, right? 11.9 into dielectric constant of free space is 8.85 into 10 to the power minus 14. The phi fv value I have just calculated, right? 0.347 divided by your q is nothing but 1.6 into 10 to the power minus 19, and your na, what was the value of na that was given in the question? It was 10 to the power 16. 10 to the power 16, correct? So the moment you try to find out this value, right, your xdt value that you will be getting, it will be coming pretty close to around 0.3 into 10 to the power minus 4 centimeters. So this is the value that you will be getting, correct? Now I know xdt, and what did I tell you? The moment I know the value of xdt, I will substitute it in the formula of Siemens dash, right? So now let me write the formula of Siemens dash, and then we will be done with this question, right? So now what is Siemens dash? Siemens dash is nothing but the formula for Siemens dash was around like epsilon ox divided by T ox plus epsilon ox by epsilon s, right, into x dt. Let me substitute each and everything, and then we will be done with this question. So now what is the value of epsilon ox? Epsilon is nothing but 3.9 for silicon dioxide. Then we have 8.85 into 10 to the power minus 14. Then we have a thickness of oxide. What was the thickness that was given in the question? 18 nanometers, right? I have to convert everything into centimeters, so I have to multiply it by a factor of 10 to the power minus 7, right? Now I have epsilon ox by epsilon s as well. Epsilon ox is 3.9, epsilon s is 11.9, and xdt value I have just found out, 0.3 into 10 to the power minus 4, right? 0.3 into 10 to the power minus 4. So everything is known in this equation, right? So the moment you calculate this value, your Siemens dash value will come out to be around 2.925 into 10 to the power minus 8 farad per centimeter square. Not too hard, not too easy. We had to use 3-4 formulas, and we jumbled between the formulas, right? We found out that to calculate the value, to use this formula, needed to know the formula of the depletion width, to needed to know needed to get the value of depletion width, and needed to know the formula of this phi fp, right? And that's why we continue to do the back substitution. So I hope this question was very much clear to you. So I'm done with the PPT today. My lecture slides are completely over now. I don't have anything else to solve today. So you guys are feel free to please feel free to ask if you guys have any doubts. If you guys don't have any doubts, then we are happy to close the session. We still have 10 minutes with us. So thank you guys. Please feel free to ask any doubts if you have. Any question or any concept part that you didn't understand in today's lecture? Was there any question that you want me to repeat? Great. Umesh, was it everything clear? Swadesh and Umesh, do you guys have any doubts? If your microphone is not working, then please type in the comment section. Like, was everything clear?